So, hello NMR community and welcome back. Last time we concluded our general discussion about Hamiltonians, and this time we want to move closer and closer to our final objective, and that is understanding how Hamiltonians are affected by magic angle spinning in solid state NMR. And this first thing in order to do this is to understand the concept of rotations and why rotations are so important and ubiquitous in the theoretical treatment of solid state NMR. And the second thing we want to understand in this video is, so far we have learned some of the some Cartesian expressions for the most common Hamiltonians that we are going to encounter. But this time we will learn that this Cartesian expression is rather not that easy to deal with in the context of rotations. Especially it's rather tricky and rather cumbersome to rotate Cartesian expressions for the Hamiltonian. So we will understand why there is a need for finding a better basis, a better notation for the Hamiltonians in which we can really treat rotations more easily. So let's jump right into it. And the first thing we want to see is that in general, an NMR Hamiltonian can always be divided into two parts, a spatial part and a spin part. And what are these two parts? Well, the spatial part, it encodes all the information about, for example, the orientation dependence of our interaction. And the second part, the spin part, actually contains all the information about our relevant spin operators that are making up our Hamiltonian. And in this context, what is actually magic angle spinning doing? If we think about it, magic angle spinning is just rotating our sample around a certain axis inclined by the magic angle. And what is the effect of this rotation? Well, we are not doing anything else than changing the orientation of our interactions in a molecule. And what does this mean? That we are just changing or performing some rotations on our spatial part of the Hamiltonian. So in summary, sample rotation can be understood as a rotation of the spatial part of the Hamiltonian, and also sample rotation in the case of magic angle spinning introduces a time dependence on the spatial part of the Hamiltonian. But also the spin part of the Hamiltonian can actually be rotated. And how can it be rotated? Well, it's rotated by the RF interactions, right? When we pulse into our sample, what we are actually doing is that we are performing some rotations on our spin operators. We are changing the orientation of our spin operators. And this will actually, an RF pulse will introduce a time dependence on our spin part of the Hamiltonians. So what do we actually learn from this slide? Well, be it magic angle spinning, be it RF irradiation, which are two of the main components of solid state NMR. In both cases, we are talking about rotations of the spatial, rotations of the spin part. And by this manner, it should become clear that rotations are really at the heart of solid state NMR. And now let's think about how rotations are treated mathematically. And if you have a mathematical object, you can always rotate it from an arbitrary position in space into another arbitrary position in space by using the so-called Euler rotations. And the Euler rotations are actually a set of three consecutive rotations that we are performing on our mathematical object. And you actually see a schematic of these three consecutive Euler rotations on the slide here on the side. And you see the first thing we do is we take our object and we rotated it by an angle alpha around our z-axis. What we then do is we rotate by an angle beta about our new y-prime axis. And in the end, we rotate by an angle gamma around our new z-prime axis. And the general concept is really that when you perform these three rotations by these angles, you can really reach any point in space. And mathematically, each of these rotations can be described by a rotation matrix R. And when you combine all the three rotation matrices, so you just multiply the three rotation matrices, then what you really get for the full description of the three Euler rotations is this really cumbersome looking rotation matrix here on the bottom. And now let's think a little bit more in detail on how we would effectively rotate a Hamiltonian. And we use the example of a spin-field interaction. As a reminder, you have here the general formula for the spin-field interaction here on the top. And the first thing we could do to simplify the treatment is that we transform this expression into a new notation which we call the scalar product notation. And in the scalar product notation, what you basically do is you take all 9 components of our coupling matrix A, so this AXX, AXY, and so on and so forth, and you put it in a 1 to 9 vector that you can see here on the bottom. And then you do exactly the same thing with your spin operators and with your magnetic field components. You just multiply all of them out, and what you get is then a 1 to 9 vector again, where you just pair the IKX with the first component of the field, so BX, then IKX with the second component of the field, and so on and so forth. So basically what is happening in this is nothing else than you're just taking the full expression, we are rewriting it in a vector form, such that whole Hamiltonian is nothing else than the scalar product between our vector with the components of the coupling matrix and our vector with the components of the field and of our spin operators. And now you would ask, why is this actually convenient? Why are we doing all of this? Well, it's convenient because when we have a vector, it's very easy to rotate it mathematically, because the only thing you need to do is that you take your rotation matrix, you multiply it with a vector, and then you just directly obtain your rotated vector with the angles that you actually wanted to rotate it with. And this is explained down here on the last formula. As you see, you just take, if we want to rotate our coupling matrix, you just take the vector with the 9 elements of the coupling matrix and you multiply it by an Euler rotation matrix R tilde, and you obtain our new rotated vector. So far that sounds great, doesn't it? But actually, if you look more into the details, it becomes rather tedious and rather quickly. And why is that? Well, first of all, the first major complication is if we want to rotate this 1 by 9 vector, we cannot use just the normal Euler matrix with that is a 3 times 3 matrix. What we actually need to do is that we take our Euler matrix that we learned 2 slides ago, and we expand it in such a way that it becomes a 9 times 9 matrix that is also able to rotate a 1 times 9 vector. And it's done in principle by a direct product. You don't need to look at the details here. You just have to imagine that if already our rotation matrix, our normal Euler rotation matrix, the 3 times 3 matrix, was tedious and horribly looking, just imagine how bad looking the 9 times 9 matrix is going to be. Now comes the whole catch about it, because there is a simpler way of doing this, and we anticipated quite a few times. The actual problem of why the problem is so bad is that we're using at the moment Cartesian coordinates. And in Cartesian coordinates, just our rotation matrix is a full 9 by 9 matrix. But now think about it. If we find the right symmetry adapted basis set, we could actually make our rotations much easier. And this symmetry adapted basis set is going to consist in the spherical tensors that we already mentioned a few times. So when you write your Hamiltonians in spherical tensor notation, what we're going to look at in a lot of detail in the next video, and we will formally learn how this is done and what we need to be aware of. Well, in this new spherical tensor notation, you're actually taking your coupling matrix and you're dividing it into sub-objects. And each of these sub-objects has a different rotation behavior. What do we mean by that? That we have a part of the coupling matrix that is transforming like a constant. And how does a constant transform? Well, it just stays constant. Then you have a part of your coupling matrix that is transforming as a vector. And then that's easy because you're just rotating a vector, so you just multiply it by a 3 times 3 matrix. And then you have a part of your coupling matrix that will transform like a symmetric matrix. And also there, it's a much simpler way of rotating this object. So you can imagine that when you choose to use a spherical notation for your Hamiltonians, we get from this horrible 9 times 9 matrix times our 1 times 9 vector, we get to a much simpler block diagonal form of our matrix, where we have a lot of elements that are actually 0, so a lot of elements that we don't consider. And you see it here by the color coding. Each of these sub-blocks of our rotation matrix will rotate a different part of our coupling matrix. So to wrap it up for this time, what did we learn in this video? Well, we have seen how it would be in theory possible to take a Hamiltonian and to rotate it in Cartesian coordinates using Euler matrices. But then in a second step, we have learned that rotations in Cartesian coordinates become very cumbersome. You remember, because we have these 9 times 9 matrices, rotation matrices that we would need to use. And then in the end, we have learned that if we would take a spherical tensor notation for our Hamiltonians, meaning that we are taking a special symmetry adapted basis set in which to rotate our Hamiltonians, then the rotation becomes much simpler, because you're taking your full coupling matrix, you're subdividing it into blocks that all have a different rotation behavior, and then your rotation matrix becomes much simpler because you just rotate the individual blocks. And this concludes our discussion for today. You can find the link to the next video here on the bottom. I thank you again, as usual, for being with me, and I hope to see you next time. So until then, ciao!